Hello. Today we're looking at elastic potential energy. During the film, there are questions, and when you get to those, if you could just pause the film, see if you can answer the questions, and then you can continue the film and see if you got them right. At the end, when you've finished, if you can complete the quiz. To start with, though, you'll need to have a calculator and a pencil and pen. So if you go and get that, and we'll continue when you're ready. Kinetic energy. Last lesson we were learning about kinetic energy. So, some questions for you. What is kinetic energy? What is it kinetic energy measured in? What is the equation for kinetic energy? A car with a mass of 1500 kilograms travels at a velocity of 20 meters per second. What is the kinetic energy of the car? Okay, pause the video, go and give that a go. Okay, kinetic energy is where objects are moving, speeding up or slowing down, such as a car moving. Anything that's moving has got kinetic energy because it is moving. Kinetic energy is measured in joules. Remember that comes after James Prescott Joule. There he is. He was the one who did the experiments with energy and who had the units named after him. This is the equation for kinetic energy. Kinetic energy is half mass times velocity squared. And here is our question. A car with a mass of 1500 kilograms travels at a velocity of 20 meters per second. What is the kinetic energy of the car? First step is you need to write down your equation. Energy is half mass times velocity squared. Then put in your numbers, like so. Now this is when your maths comes in. Remember BIDMAS, so the order that you should do things in: brackets, indices, divide, multiply, add, subtract. Whew, there you go. So we can want to square the 20 first, then multiply it out, come up an answer of 300,000 joules, which is 300 kilojoules. First of all, a couple of things about energy. Definition of energy. Energy is what you need to make things happen. It's also sometimes defined as the ability to do work. We can think of energy as existing in different energy stores. There are 8 different energy stores. Energy cannot be created or destroyed. It's just moved from one energy store to another. When this happens, work is done. Work, like energy, is measured in joules. Here we have our different energy stores. We've got the magnetic and electrostatic, kinetic, thermal, gravitational, chemical, nuclear, and elastic. And then we've got a stretched rubber band. So if you stretch something like a rubber band or a spring, you can store energy in it. But rather than me talk to you about this, let's go and have a look at this clip and give this a watch.
Energy is the capacity to do any work. Potential energy is a form of energy that an object possesses by the virtue of its position. Another way to think of it is as stored energy that has the potential to do work. Potential energy can be one of 3 types: gravitational, elastic, or chemical. Our focus for this session will be on elastic potential energy. Elastic potential energy is the energy that is stored in elastic materials and objects such as springs and rubber bands. If we compress a spring, the force we apply to it will be stored in the spring as elastic potential energy. Once we move our hand, the stored energy will be released, helping the spring bounce back and return to its original position. We can observe a similar phenomenon when we stretch the spring. The stored elastic potential energy will help it restore its original position once we release it. A stretched rubber band also acquires elastic potential energy. The further it is stretched, the more potential energy it has. Let's look at a bow and arrow. When the string of the bow is pulled, the bow, which is made of a flexible material, will bend and store energy. Once the string is released, the energy will also be released, launching the arrow. The further back the string is pulled, the more the bow will bend, allowing the arrow to travel even further once the string is released.
Okay, many objects. Many objects are designed specifically to store elastic potential energy. For example, wind-up clocks, an archer's stretched bow, a bent diving board just before a diver jumps, the twisted rubber band which powers a toy aeroplane, a bouncy ball compressed at the moment it bounces off a brick wall. In earlier generations, wind-up mechanical watches powered by coil springs were popular accessories. In fact, if you look in the past, there were lots and lots of clockwork toys. Look at that car. Okay, let's take a closer look at elastic potential energy. The equation for elastic potential energy is E equals half k E squared. I'm going to put a little subscript on the E here to indicate that is elastic energy. Now E is elastic energy, which is measured in joules. K is the spring constant, which is measured in newtons per meter. And E is the extension, which is measured in meters. So there really is a lot of E's in this equation. E equals half k E squared. Let's have a look now at the spring constant. Now the spring constant represents how difficult it is to squash or compress a spring. So let's think about some different springs and think about the spring constants. Now a pogo stick will have a very big spring constant, because obviously there's something, I don't know if you've ever seen one or not, a person climbs on here and they have to like bounce up and down on these bits. It reminds me actually of another thing. I don't know if you've seen this one either. See if you can guess what it is. This was called a space hopper, and it was usually bright orange. And it was another sort of thing that you'd bounce up and down on. But instead of having a spring, it would be made out of rubber, plastic, and you'd bounce, you'd kind of attach yourself, you'd sit on it, and you'd pull its ears, and you'd bounce up and down on it. So, although it didn't have a spring in it still had a spring constant, depending on how easy it was to compress it. And then something like, well, every physics teacher's favourite object, of course. The slinky. So in terms of the spring constant, the pogo stick would be highest, then the space hopper, and then the slinky, because that's really easy to stretch. And remember the equation that goes with it, E equals half ke squared. A quick word about the extension. Measured in meters. If I have a spring, and we stretch it, maybe you add a weight to it, well, the extension is the amount that it has stretched. So the extension is going to be that length there. And remember our equation? Elastic potential energy. That's the equation for elastic potential energy we've just looked at. Let's have a look at an example. A rubber band is stretched from its resting position a distance of 0.1 meters. If the spring constant is 2.5 newtons per meter, how much energy is stored in the rubber band? Okay, to solve this, the first thing you do is to write out your equation. E equals half ke squared. Next, put your numbers into the equation. Remember, brackets, indices, divide, multiply, apply, add and subtract. So we need to multiply out that 0.1 squared first. And don't forget the units, which is joules. Okay, here are some for you to try. Pause the video. See if you can work these ones out. Let's check the answers, see if you've got those right. If a spring is stretched a distance of 0.25 meters, how much energy is stored in it if the spring constant is 80 newtons per meter? So same as before, write out the equation. Substitute the numbers into the equation. Remember the bid mass. Don't forget your units. Second question. What is the spring constant of a pogo stick if its spring is compressed 0.2 meter and it stores 70 joules of energy? So same as before, start off by writing out your equation. Substitute your numbers into the equation. And for this one, we have a little bit of algebra at the end. K is going to be 70 divided by 0.02. So K is 3,500 newtons per meter. Thank you for watching this video. Now complete the quiz.